Talking about awesomeness. No, I wasn't talking about myself. No, we were talking about full point vortex methods right on your iPhone or iPad. But today, what we're going to do is solve some PDEs in class with MATLAB. I'm going to do it right here on the laptop. And basically, I want to show you what it means to violate a CFL condition. Okay, so we're going to take some of these methods we've been talking about, program them, and then actually take a look at the dynamics, violate CFL, see what happens when you have an unstable scheme. Okay, so a couple things to keep in mind. We're going to look at two equations in particular. UT equals UX and UT equals UXX. Those are the two prototypical equations we've been looking at. Second, since we need derivatives, first derivative or second derivative, remember that we have derivative matrices. Let's make one of the U of X matrix is going to look something like this. 1 over 2 delta X, 1s, minus 1s, 0s. And if I make periodic boundary conditions, I get a minus 1 here and a 1 there. This is the first derivative matrix, one-dimensional, periodic boundaries. Now, you recognize the structure of that matrix, right, hopefully, because when you do the matrix A and the matrix, is it B or C, whatever, that's the basic block that sits there moving along things. Okay? Periodic boundary condition in X. Then there's UXX, which is 1 over delta X squared, and then this matrix has minus 2 on the diagonals, 1's on the off diagonals, 1's in the corner. Okay? So we're going to need those, because we're going to be solving these. And these things here are basically what we're going to use to calculate the derivative, propagate forward in time. Okay, finally, let me write down some schemes that we're going to implement, and so that we have these in our head. So for the wave equation, I'm going to talk about, we're going to basically looking at leapfrog and Euler. Those are the two. Okay? So if you do the one-way wave equation, leapfrog 2, the one-way wave equation looked like this. The solution in the future is what it was now, plus lambda over 2, un plus 1, m minus u, n minus 1, m. There we go. And remember here, I'm going to take c to be 1 in these equations, so the lambdas in this are going to be just delta t over delta x. And in the leapfrog, something similar. There it is. So that's for the wave equation. Those are the schemes. Now, what we know for the wave equation, this is always unstable. This is stable for lambda less than or equal to 1. Okay, those are the results for the wave equation. Now, for the heat equation, let's write down the schemes. The schemes in the heat equation are, here it is for Euler, again, and for leapfrog 2. And for the Euler, you get u of n m plus 1 is equal to u of n m is equal to lambda, and now you have u m plus 1 minus 2 u of n plus u of n minus 1, and all these evaluated at m. And now lambda is equal to delta t over delta x squared. That was Euler. And that was stable for lambda less than or equal to half. Okay? And then for leapfrog, it was u of n m plus 1 is equal to u n m minus 1. And then plus 2 lambda. Oh, that's a plus lambda there, not an equal. Plus 2 lambda, and then that same thing there. Okay, so those are the two schemes. Yes?
I think you need
What's that?
the heat equation should be on the top, right?
No, this is a heat equation. It's two derivatives, right? The heat equation has two derivatives, right? So you have point in front, point behind, minus 2 the twice point. The wave equation is just neighbors, right? So these are the u of x terms. These are uxx terms. Okay. So that's what we have for schemes. Now what we're going to do is program each one of these up. We're going to start off the wave equation, program this up. We're going to see what happens if you use Euler. It's always unstable. And we're also going to program up leapfrog. And we're going to see, okay, it's stable for lambda less than 1, so we'll do both and just try to get a look at what happens. Okay? So that is the objective for today. So let me pull this down. Mostly going to be on MATLAB today. All right. Can we get our mood lighting up here? Sweet. All right. All right. Okay. I could do my Barry White voice now. Let's program some MATLAB. All right. So let's open a file. And I think we have, what was I calling this thing? Was I calling it? I think that was the program. That's what I had open before. Yeah, okay. That was the last time we did something. Okay, there we go. So first of all, start off our code with programming with commands such as these. And let's actually, let me try to get this thing to be a little smaller here too. Okay. Clear all, close all, CLC. Now what we're going to do is the one-way wave equation. So things we need to do. Okay. All right. So things we need to do is first we need to do a few things like initialize the grid. Right? So how we're going to chop things up, our time steps, and what our CFL number is going to be. So let's go ahead and decide to run this out for, let's say, time equals 4. We're going to go from time 0 to 4. So we're going to pick our final end time, which will be 4. Okay? And what we're going to do is pick our domain. Let's make it size 20. We're going to chop it up into 200 points. Okay? Everybody can see that all right? All right, so we have our time, we have our domain, how we're going to chop it up. Remember, these periodic boundary conditions, we're assuming these matrices, so we have make a vector, x2, which is a linear space that goes from negative L over 2 to L over 2 in n plus 1 points. Okay? The last point is the same as the first, so really what we want is x, which is equal to the first 1 through n of these things. Everybody okay with that? All right, so we kind of had our grid, chopped it up. We've decided. By the way, in doing that, we then have a dx. The dx is how finely chopped. When we picked a domain of size 200 and we chopped it up into 200, that picks up our dx, which is just the difference between any of those 2 points. Okay? So we have dx. Now dx is going to play a big role in our CFL, right? Now let's pick a dt. I don't know, let's make something up. Pick dt is 0.2. We'll take a look at our CFL number in a minute. In fact, we can just do CFL is equal to dt over dx. And let's go ahead and run this at this point. Run. And CFL is 2. Okay, so now if you go back to the board, CFL 2, nothing's stable for a CFL of 2. But fine, let's just work with it, roll with it right now. We'll make it 2. If we want to make it 1, and if we want to do Euler, we have to cut that dt in half. Okay? But you see, I have full control right there of setting all the dt's, all the dx's up. Now my actual time, it's going to be important now, is my time variable is going to go from 0 in steps of dt all the way to time 4. Okay? Everybody go with this? So this is how I'm going to step. Now notice, again, we're not using something like OD45, which we just say, give me the initial time and final time. It figures out its dt. We are now controlling it. We're setting up one of these algorithms, okay, to do it. So I've just discretized time and space, and I have a CFL. Okay. Step 2 in all this process is to, before I can start this thing off, I have to have an initial condition. Okay? So let's define an initial condition. My wave at time 0, let's call it u naught, let's just make it a bump. This is an easy thing, a Gaussian. So let's go ahead and plot what x u naught looks like, just in case you forgot what your Gaussian looks like. Here it is. That is our initial condition, a bump. Now, it's the one-way wave equation, so this thing here is going to be a wave that's going to move one way. Okay? So there we go. It's going to be a very simple-looking thing, but fine. We got this wave. All right. Now, let's go ahead and do, for the moment, not leapfrog, but Euler. What Euler says is you give me an initial time. So leapfrog is different, right? Leapfrog requires 2 slices of time to get going, right? Your time in the future is what it is now, plus you also have something, sorry, the time in the future is what you had 1 time step ago, plus some stuff at the current time step. So you need kind of 3 levels. Euler just says my solution in the future is what it is now plus something. So I can use all my current points to generate the future. So let's just do leapfrog. And here, by the way, is my starting point for the iteration, or starting points in space. Okay, U naught defines this Gaussian, and I'm going to march this Gaussian forward in time according to the Euler scheme that we had before. Now, before we proceed too far down this road, we need the derivative matrix. Okay, and this is pretty easy to build. You make a set of 1s, which are n by 1, and then you say A is simply equal to SP diags, and you have negative 1s, and you have 1s, and they're located at negative 1 and 1, and this is an n by n. Okay, and you have on the corners, on the first corner, A1n, you have a negative 1, and on the bottom corner, you have a 1. So this here is my 1 derivative matrix, second order accurate, periodic boundary conditions.